Welcome back to this session. What we are going to look here is first we are going to revise some of the concepts that we have done so far to understand where we stand in terms of what we call is classical thermodynamics. Then we will enter today into the realm of what we say as the statistical thermodynamics. As you know, the whole idea about molecular dynamics is connecting microstates to macro state, and that whole idea came about with the understanding of statistical mechanics. And as you know, statistical mechanics still follows to the most part in the realm of Newtonian mechanics in case of molecular dynamics, but that was also the beginning of quantum mechanics. And I think that's an important switch which happened from the classical ideas into what we call the modern physics or the quantum physics. And so we will touch upon that, although molecular dynamics essentially remains itself into the realms of classical mechanics. But there are certain effects that we will consider as we move forward, which are quantum effects, and at that point we will define what are those effects that we should be worried about. So, if you look at the slide, we started with the classical thermodynamic concepts of the system, a closed system, an open system. We also looked at some of the extensive and intensive properties. And as you know, important aspect here to point out is that the state space, or what we call phase space, is dependent upon the state variables, and those state variables are the thermodynamic variable, which are of two kinds, extensive and intensive. Extensive variable change with the size, intensive variables do not, and those are pressure, volume, temperature, specific heat, and few other variables that you will come across. And that's when we said, okay, a thermodynamic system we can define in terms of state variables, pressure and volume. Then we started looking into the gas laws, where we said Boyle's law connects between pressure and volume. Avogadro's law connects between volume and number of atoms or number of molecules. And then we looked at Avogadro's number, which is a quantity that gives us good idea about average number of particles in 1 mole of the substance. Then we also looked at the relationship between volume and temperature, and that's where we looked at the Charles law. So now we have relationship between all three state basic variable, pressure, volume and temperature, using the ideal gas law, as well as the number of moles of substance, which is PV is equal to nRT, R being the universal gas constant. So, with that understanding under our belt, then we started looking into laws of thermodynamics, and we looked at 4 different laws of thermodynamics: zeroth law, first law, second law and third law. And we said that the first law of thermodynamics connects the heat as well as the work with the statement of conservation of energy. So, work can be converted into heat and heat can be converted into work with a particular proportionality constant. So, we said those are the two ideas, heat and the work. While they are interchangeable, there is also something called internal energy of the system. So, you have to provide heat as well as work to change the internal energy delta U, and so we came up with generalized equation Q plus W, Q being heat, W being work, is equal to delta U. Now, this positive sign can become positive or negative depending on what kind of system you are looking at. So, although you will see the same equation in some places, Q minus W is equal to delta U, and that is if it is a closed system. So, do not get confused. The sign will be dependent upon how you define the system, and with that we looked at the thermodynamic phase space, again PV and T. You also looked at the 3-dimensional space of PV and T, pressure, volume and temperature, and looked at the 3-dimensional phase transition. So, we looked at how the liquid can become gas, or solid can become liquid, or from solid to liquid to gas, and that is the point we made right at the beginning of this course, saying that molecular dynamics, using a very simple potential energy function, we can traverse the space from both liquid, solid and gaseous phases, and I think that is the power of molecular dynamics. If you look at, then we understand the reversible and irreversible processes. So, once you move ahead of the first law of thermodynamics, then immediately we need to look at the specific heats as well as we look at the losses that are happening because of irreversible process and bringing the concept of what we call the entropy. And entropy is the quality of the work that is being done. That says is that are there more losses, or a system going from disordered space to ordered space or from order to disorder. So, order to disorder transition and the losses of different kind which are accounted for, some of that concept goes into a definition of the quality which depends on the temperature parameter, and so S, which is entropy term, is also introduced here. And then we said is that there could be compressible or incompressible substances, and then the specific heats change based on the if it is compressible, then you will have two different kinds of specific heat, CV, which is for the volume, and Cp for the pressure. And then if you look at here, we can also define then the inequality due to the entropy, which says that it will be above 0 or equal to 0, will never become negative because the entropy always increases. And then finally, we looked at 4 different processes: isothermal, isochoric with the constant volume, isobaric with constant pressure, and then adiabatic process where we looked at a nonlinear transition from pressure and volume curve with the exponential term gamma. So, if you look at in terms of the laws of thermodynamics, let us revise them very quickly, and then we will launch into some of the ideas that we want to now today talk about, different kinds of thermodynamic situations and ensembles that we are trying to come up with the statistical mechanics understanding. I know I am covering a very broad range of topics, and I am also assuming that most of the students in this course do not have prior experience with a lot of these concepts. So, that is why I am coming up with all the basic concept first, building it up to the molecular dynamic simulations. So, let us first look at the 4 laws. 0th law says that if 2 systems are in thermal equilibrium, then third system they are connected with will also be in equilibrium. So, what it says that you can essentially construct a thermometer, because if you put a device which is going to measure temperature, and if you connect it with the substance that you are measuring temperature, then what you will see is that the temperature will be equal in the thermometer, and that is why you can measure. First law again is a conservation of energy. So, work going into the heat and heat going into the work, and also increase of the internal energy. Second law is important because if you look at the statistical mechanics as well as classical mechanics, most of the things will be related to what we call is entropy, and that is why the quality of the energy is very important. It is not only quantity of the energy, but also quality. And what we mean by quality of energy is at certain temperature differentials you may get much higher efficiencies of conversion than at the lower temperatures, and that defines a limit for how much conversion you can get out of based on certain temperature systems, and that is where we also define something called Carnot efficiency, which we will talk a little bit later. And the third law says that net entropy changes in any process tends to 0 as the absolute temperature also goes to 0. So, it almost says that it is very impossible to get 0 degrees Kelvin level, because that is where we get the thermodynamic limit. So, let me with this kind of introduction and revision review of the concept that we have covered, we are now going to launch into some of the advanced concepts of what we call as thermodynamic potentials, where you will look at the internal energy, the Gibbs free energy, the Helmholtz free energy, and how those potentials are important for some of these thermodynamic transitions, and in particular some of the very important phase transitions both in liquid, solid and gaseous phases. Thank you.